All right, let's walk our way through a stoichiometry problem just for the purposes of refreshing our memory on this stuff. Now, those of you who took chemistry with me last year will recall that when we did stoichiometry, we tended to do one giant process that ended up at a particular result. We're going to approach this from a slightly different perspective where we're going to do it piece by piece. Okay, so over here I've got some kind of targets I'm looking at. I got a reaction up here. It's balanced with the coefficients that are red. It's iron, like solid iron and oxygen gas making rust, essentially, making iron oxide. Now the way this works is we usually have some sort of measurement at the beginning. For example, 20 grams of iron. And what we're going to say is that there's excess oxygen, so there's more than enough oxygen for this reaction to happen slowly over time. And what we like to analyze is how much rust it will produce. So we're basically targeting those two things. So the first thing you want to do in any stoichiometry problem is make sure you're analyzing the right compounds or elements. So in this case, we're going to be looking here, we're going to be looking here, and we're not going to pay attention to this. Okay, we're saying there's more than enough of this for the reaction to occur, but we don't have a specific measurement, and we're just not going to analyze it at this moment. Okay, so we have 20 grams of iron. We want to know what it's going to produce of iron oxide. So let's take a look at how we would set this up. The first step we're going to do is we always take our starting measurement and we want to convert it to moles. Okay. So we're going to write out 20 grams of iron, and we're going to convert it to moles, okay, which means grams is going to have to go down here. We look on the periodic table at the molar mass, and we'll do a little bit of rounding here. We see that iron is around 56 grams. So it's going to be 20 divided by 56. And that gives us about 0.357, and we'll just round it off, 0.357 moles of iron. Right now I'm not going to be too concerned with significant figures and how much we're going to round it. We just want to look at the process. Okay, so 0.357 moles of iron. 0.357 moles of iron. So this 20 grams of iron really equates to way less than 1 mole of iron atoms. Okay? Now, what we can do, instead of doing this as a long, drawn-out process and keep adding steps onto here, is we can just use our previous result as the next starting point for another conversion. So if I take this and I use 0.357 moles of iron, see, notice that number now represents moles. We're done with grams. We've already converted that. I can use it to get my next piece. Okay, what I'm going to try to do now is, once I've converted this to moles, I can convert it to anything else within the reaction. I can compare it to any other compound or element that's there, as long as I have a balanced equation that relates the two. So I'm going to try to kind of focus my efforts here. I'm going to take a look at iron oxide. I would like to turn moles of iron into moles of iron oxide. I would like to relate those two numerically based on what I see in the reaction. Now be careful with your labeling here. Moles of iron oxide goes on top. I need moles of pure iron to go on the bottom, because that way they'll cancel out. And then these units will tell you where to get that relationship. Okay? That relationship comes from the red numbers that I see up here. Those coefficients. 4 moles of iron will produce 2 moles of iron oxide. So this is a 2 to 4 relationship. Now why did I put the 2 on top? Because 2 goes with iron oxide, and here's a 2 with iron oxide. Those two things have to match. 4 goes wherever iron is, so 4 goes on the bottom where I see iron. Now I'm just going to plug this in. I take 0.357 times 2 divided by 4. Obviously you can simplify that. 0.357 times 2 divided by 4. I get 0.179. I'm going to round this a little bit. I get 0.179. Now look at what that represents. That is moles of iron oxide. So I'm going to put 0.179 right there. Moles of iron oxide. So I've converted 20 grams of iron into moles of iron. Then I went through a process to convert moles of iron to now moles of iron oxide. So now I've changed it from one substance in the reaction to another substance. And now I'm going to convert it back to grams, which is something we can measure and compare fairly easily in a lab. So I'm going to take this stuff right here, 0.179 moles of iron oxide, and I'm going to begin with that. 0.179 moles iron oxide. It's really important that you label your amounts accurately so that you don't get mixed up on what number something might represent. So I'm going to turn moles of iron oxide now back into mass, into grams. And I'm going to take moles of iron oxide and put it on the bottom so it'll cancel out. So now those are gone. And where do I get this information? Well, once again, anytime you are looking at grams per mole, it's grams per 1 mole, and that's what we find on the periodic table. So I got to go through just like I did up here, and I found the weight of iron. Now I got to find the weight of iron oxide. Okay, so let's just double check our work here. Iron, if we look it up on the periodic table, weighs 56 grams per mole, but there's 2 of those in this compound. Oxygen is 16, but there's 3 of those. I've got to put all that together. Okay, 56 times 2 is 112. 16 times 3 is 48. If I put those together, I get 160 grams per mole. So 160 goes right there. Okay. Now when I look at this, all I really have to do is take 0.179 times 160. That 1 doesn't affect the math. And that should tell me how many grams of rust will be produced from this reaction if we had the amounts that we intended to start with. 0.179 times 160. And I get 28.6, roughly, okay? Obviously I'm doing some rounding. I'm not too concerned about significant figures at this point. What did I just say? I said 28.6, okay? Be careful of what this means. 28.6 what? It represents grams of iron oxide. So 28.6 grams of iron oxide. And what we've done is essentially a 3-step process. We started with 20 grams of iron, plenty of oxygen for this to happen, no specific measurement, but just lots of it. And we want to know how many grams of rust are produced. We turn grams to moles, then to moles of iron oxide, and then back to grams. Now those of you who took chemistry last year, you remember doing this all in one giant process where we go grams to moles to grams, all at one big process. This is another way of approaching it. If you kind of get turned around in the whole thing and don't exactly know how to put it all together at once, you can do it piece by piece. Grams to moles, take those moles over here, moles to moles of something new, take that answer over here, moles back to grams of whatever I'm dealing with. Okay. And that's just a quick little refresher on how to do stoichiometry within a reaction. Now, there may be times, depending on what you're looking for, where all you really needed was this amount for some other particular application. Or you might be working your way through the problem and you would like to finish off with moles of iron oxide because you may be turning that into something else, say when you're dealing with gases or solutions. So you won't always end up at grams, but that's a typical way to go just because grams are easy for us to measure. But there are applications where you might stop here or you might stop here. Okay. And there's also another way we could take this to start with and we could find out how much oxygen would be needed. We could go back and redo the entire problem. First step would be exactly the same because it's just iron, but then we could get right to here and we could change this to oxygen gas, different ratio, and all of a sudden we would know exactly how much oxygen gas we would need at the very end of this process as well.